Good afternoon and welcome to the last session of the day here on Wednesday at MTS. In this session entitled Greener Pipelines and Smarter Conversations, Responsible Innovations in Media Technologies. So our first two speakers in this session will be Shreejith Shanker and Helios Lyon. So Shreejith, he's an assistant professor in the reconfigurable computing at Trinity College Dublin, Ireland, and he leads the research group on reconfiguring computer systems. His research interests include reconfigurable and adaptive computing systems in network computing, post-production, media workflows, design automation tools, and many more things. And then his co-author and co-speaker, Helios Lyon, he's from Disguise, and he's an embedded software engineer who works in the IP video, on the IP video formatting card and hardware integration that's used in venues such as the Sphere in Las Vegas and in Eurovision. So please welcome them to the stage.
Thank you, Thomas, for that introduction. So I'm Shreejith. As introduced, I'm an assistant professor at Trinity College Dublin, and my work is mostly on FPGAs, which is the configurable computing fancy word, but essentially, digital design. And Helios here, who's with me, is from Disguise, and we are jointly working through a European project called Emerald. The idea of the project is to evaluate the impact of AI in motion picture workflows and particularly focusing on the energy and sustainability aspects of it. So today we're going to talk about energy monitoring in visual processing pipelines. Obviously, why energy is important. Media is a very massive industry, which is also compute and network heavy. According to some stats, video accounts for over 80% of the internet traffic. That was pre-pandemic, and post-pandemic, that number has significantly grown as well. There was a study from Albert Institute in the UK where they determined that a single tentpole film consumes about 2,800 tons of CO2. And this is always going to go up, especially when we start using AI at different stages of your workflow. So from pre-production to post-production to previous, post-this, etc. And obviously on the content distribution side as well. And obviously we look at virtual production as another domain where we see having the energy being impacted. Now the problem with measuring is that there's no standard tools / standard ways of measuring the impact of any of these computing techniques, or to compare which one is better than the other. Obviously, there are tools which allow you to do that, but there's no standard way of saying, okay, what is the impact of instruction being executed as opposed to instruction B, which might be better, and so on. And this is critical when we think of designers of tools or designers of algorithms, right? So they need to know how to write the algorithm better, how to format the tool better, how to compile the tool better, to achieve that additional level of optimization to improve the energy footprint. So our aim within this project was to develop some frameworks which allow you to establish some energy baselines for existing systems, and to figure out ways of understanding energy consumption from a developer perspective as well. So that's the two parts of the puzzle that we're trying to do, and hence the dual approach, right? So as I mentioned, there are workflows which exist, which allow you to profile applications. So NVIDIA has a set of tools, Intel has another set of tools, and they allow you to profile, instruction pipelines, how to compile your instruction sequences or order your instructions in such a way that, your memories are most efficiently used, and so on and so on. but energy is never factored into that equation, right? So it's always extracting higher performance, not hitting memory bandwidth and stuff like that. Again, on the media server side of things, there are remote access mechanisms like IPME, which allow you to gather some level of information on what is the power consumption, especially if you have a PSU sensor, or if you have things like smart PDUs, power distribution units, where you can extract this information about how much energy is being consumed in near real time. But again, there has not been much work on validating how accurate these are, or on whether the granularity that they provide is useful for tool developers or for optimizing system level. So this investigation essentially splits it into two sides of things. One part led by Disguise, where we look at existing workflows, existing machinery, existing tools and racks, and see how we can establish power consumption matrix across that. This starting from the compute side, storage, and even display, and then subsequently going into when you're deploying your tool, what happens at your processor, at your GPU, and how we can optimize that. So handing it over to Helios, who will talk about the first part on cost monitoring.
Testing, 1, 2. Okay, cool. Hi, I'm Helios from Disguise. So I was brought on to look, I think in 2023, I was approached by TCD as part of the Emerald project to look at within Disguise pipelines, which are sort of traditional XR and VR flows. How can we measure using the tools that exist already, and then how does that potentially generalize into other systems? So we tried to use as much open source tooling in this as possible. Given a full XR stage that we have in-house. So given, for example, like a max power scenario in Disguise, typically the way that the sort of monitoring is done at the moment is you're given a specification for your server, and you use this to be able to specify the generators that you might have on site, the general power requirements. You convert it into BTU in order to figure out how much cooling you need, how much air conditioning. But this only provides like a very, very high level idea, and you don't actually know how much you're consuming. You just know what you need in order to sort of not fail. We also have problems in that workflow where we use a sort of artificial tools in order to simulate max power situations, and it's not quite as accurate as we'd like it to be. So yeah, that's something we'd like to look at. We also later thought it'd be interesting to look at LED panels, because we have some, and there were some issues with that. Basically, we have scenarios where the panel manufacturers don't provide very detailed specs. They're also providing sort of steady state and max power scenarios. And these are, again, enough to specify the power that you require for your overall setup, but not enough to know how much you're actually using. So we're trying to develop a sort of content-aware system where so based on, for example, some given input frame, can you figure out how much power you're using at any given time, not only on your screen, but sort of distributed throughout your entire workflow. So that's sort of the aims that we're trying to accomplish here. So for a site manager, you might get a bit more detailed information and specify a system that's meets your needs a bit better. And then, yeah, it's also just interesting generally from an orchestration perspective and an automation perspective. So we're sort of specifically looking at a component of our servers. So I don't know, this might be the first sneak peek of the Disguise server interior, but it's really not that crazy in some ways. It's a lot of sort of proprietary independent vendors that are brought together into the servers that we make, but really our glue is our control software designer. The unique sort of element that we leverage that's not in a lot of off-the-shelf hardware is the system management controller that we have in each of the servers. this allows us to do what's called out-of-band IPMI. So in motherboards, there's typically a baseboard management controller. I say typically, there's always a baseboard management controller, and that has this sort of its own RJ45, so its own access point, and often that's not linked to the host OS. So what that means is when you use something like WMI, you don't have the implementation for your specific hardware. So you can't ask your PSU from your host OS, hey, how much power am I using? That means that like you don't really have the information that you need in order to do any sort of intelligent monitoring. So we have this additional piece of hardware. It's like this this custom board that sits in every server. It runs an embedded Linux operating system, and it queries the BMC directly using something called IPMI, the Intelligent Platform Management interface. That's sort of like a messaging system which sits on top of the system management bus, which is interface, which sits on top of I2C. There's sort of a whole layering, but these are all standard tools that exist at sort of the motherboard vendor level. I'll talk a bit more about how common they are in a bit. So if you can imagine a scenario where you have a disguised server with this embedded Linux tool running in it, it is connected to a management network, which means that all of these cards talk to each other, and you can sort of enter an IP on your management network and get this pretty UI, which says, look, here's all of your servers represented by these system management units, and then you can interact with them at a very low level. What we ended up implementing there is this sort of low-level network API where you can sort of directly send IPMI commands over the network, which we haven't seen a lot of before, and it's pretty cool. I think the cool thing here is that you can directly talk to the PSU, so you can sort of ask it based on whatever sensors it has, which are typically very accurate and have a very high sample rate, how much power it's using, and no other approaches that we've seen take into account the power supply inefficiency, which is actually, relatively important, and, a relatively large amount of the total energetic cost of the system. So that's sort of the architecture that we went with, but actually that already exists. So all of our servers, or the large majority, already have this, and so we sort of made some new firmware which can be updated on the system management controller, the SMC, and then talks to the rest of the system components at a site level. So sort of one level up, you can see the different servers that we would have in a rack, for example, and the system management controller is in each one and is connected via the management network. And so we can very easily, just with a simple Python script running on a computer connected to the management network, query these power APIs and get a broader system view. There's also a bit that I haven't talked a lot about yet, just at the top, about the current meters are running in series with the LED panels. So we found some pretty simple off-the-shelf meters, which allowed us to characterize 4 rows of our panels in a sort of content-aware way, where we're in control of not only the servers and the content that's going out and querying the power of those servers, we can also scrape the endpoints presented by those off-the-shelf current meters. So we get really quite a holistic view of what the system is doing, and that's currently running. I think, so here's just the dashboard that comes out of that. It's got a ring buffer, so this is only 5 minutes, but we can run it for significantly longer. It's just to give you an idea of the kind of visualization that you can do with this sort of power. Again, so British thermal units are up there because it's useful for integrators and site builders, but I mean, really, it's just a constant, so it's not a huge deal. But the carbon emissions, I thought, was sort of the cool thing. It's like a running tally, so you can, cumulatively over the course of your session be like, okay, this is how much I've used. And I think the interesting part there is that you can, because you have control of also what's on the media servers, run different workflows. And this is sort of the next stage in the Emerald project that we're doing, where so other people have developed these sort of energy efficiency tools that work with our software and others like Nuke. And so you can sort of run these on your servers and then characterize the difference that they make on your overall workflow. So I think that's it for that slide. That was part of our QA system. So now every time they run a performance test for a new update of their software. They can also validate if there are any significant changes to power. Not that they'd make decisions about that, but it's interesting to know. Yeah, we did a bit of an infrastructure assessment. So here's where you can see that like the AST2500 is a baseboard management controller made by ASpeed, and it's actually on all of our motherboards, which is not something we sort of planned for. It just happens to be sort of the most used. So I don't know. It's interesting that there's, a lot of common implementations at a level that people don't necessarily consider, and that those are actually quite useful. And if we think back to the sort of overall system diagram, what's cool about IPMI is that you can directly query devices that might not have sort of direct implementations in things like WMI. So if I have like a register address on a NIC or on a GPU, I can pull their sensors through this interface, and that's quite cool, and it gives you sort of a out of band image of the entire system without running anything locally. What's cool about that is that there's no real performance hit, right? We're running off a different power supply, the same power supply, but a different power line. And so it's like significantly more efficient, than running on extra threads, and potentially impacting the performance of our application. We did a bit of analysis, as well on the panels. So I said we had those, sort of 4 rows of LED panels, each with a current meter attached, and then we pull the endpoints. So we're only doing this because the panel makers wouldn't send us detailed stats or characteristics of their diodes. They wouldn't tell us exactly the way that they do it, and so we were like, shit, okay, in order to like characterize them as part of this broader effort, we need to come up with our own framework. So what we do is like we run sort of 2 tests where we set on the LED processor 2 different max brightness levels. So that's 500 and 1000 nits. We could go higher, but like it's not worth it. There's some stuff in the paper about that. And then in the software, we step through those brightness levels at different increments, so 25, 50, 75, 100%. And then we can sort of draw this power curve related to individual colors. It's interesting to do this, mainly because we can characterize a panel. We didn't get to that point. We didn't have enough data, but you could say like, look, here for this panel, this size, given an input frame, here's the energy output that we can predict. So it's very, content aware. It would be cool. We didn't end up having the enough data to that my p-value is really bad. Anyway, I need to work on it more. But yeah, I don't know. I don't think I have quite enough time, but what I was going to talk about is that we have to do a sort of inverse transform from sRGB, from linear to sRGB, because there's this weird thing that happens when you measure the power, is that in the software it's sRGB, but the linear intensity of the power as emitted by the screen is obviously linear with power. So there's a weird thing where if you see the grayed out lines, you can see that they're sort of apart, where there's different nit values for what should be the same at like 50% at 1000 nits and 100% on 500 nits. So yeah, that was pretty cool. I didn't see that anywhere else. We also saved some power while doing this, because we realized we were leaving the stage on every weekend for the entire year. So we automated that and saved a lot, which is cool. This is, I don't know if it's actually available yet. I think it's pending. There's like some licensing problems, but we're hoping to release this so that people can characterize their own panels and then give us some more info. I think that's me. So now we can move on to the granular approach from Shreejith.
Right.
Sorry, it took too long.
12 minutes. Okay, you can do this. Right. So the idea of what Helios talked about was to analyze at an entire stage, an entire setup level, what your power consumption is, how you can build automations on top of it to, essentially reduce runtime power consumption. But what about tool developers, right? So that once a tool is in production, then, there's not much you can do in terms of change, because there's a saying, if it's not broken, don't fix it, sort of stuff. And most of the industry follows that as well. So, we had this question then, okay, how do we characterize, individual tools, individual instances of tools? Can we use existing infrastructure to do this. So as Helios sort of mentioned, there's a lot of on-chip sensors on GPUs, CPUs, on motherboards, power supply units. How accurate are these? And how granularly can you get these data? Of course, we realize some of them can be as offset as 40%, and the polling rate on some of them is not great if you want to do, long-term profiling and tool-level profiling. So essentially, we did a bunch of tests to figure out what the current tools can do. So here's an example with NVIDIA tools. So our test setup is a bit old, not the greatest GPU in there, but still a fantastically capable device. So it's a 3080 Ti in the setup, and we ran a bunch of Nuke-based workflows. So Nuke is Foundry's industry-leading tool for node-based visual processing. And the reason why we used Nuke was, A, we were familiar with it. B, we had a lot of developed in-house developed tools which we could use, and obviously then 3, Foundry has one of the largest community-supported frameworks through Catry, so we could pull models from Catry and run this on the CPU and GPU as well. So here we have a graph of some of the profiling experiments. So with the Nsight compute tools, you can establish, where your bottleneck is. Is it in the memory? Is it in the compute path? And so on. So fantastic tool, right? And Intel has a similar one for CPUs as well. Now the problem is with the power consumption here. So every time we ran it, it ended up giving us slightly different value, despite the fact that, okay, we made sure we cooled it enough and all that sort of stuff. So if we take an average of about 1,000 runs of the same tool, we end up with this distribution graph, which says for the same workflow, essentially, we have some cases where we hit higher power consumption, some cases we get lower power consumption, so massive distribution. And this was polling the SMI interface, so the on-chip sensors in the GPU as well. So we did some more work, essentially developed a power monitor of sorts, which will plug into the power lines natively. So it's a bit of hardware hackery, essentially. And so that gives us the ground truth of what the measurements were, right? What is actually being consumed. And again, we ran the same sort of benchmark exercise, and we figured out, okay, there's this substantial offset. And this is not just the case with NVIDIA or the GPUs. We had same results from the Intel side of things as well, or the CPU side of things as well. Here we were using RAPL, which is one of the most popularly used power frameworks for CPU-bound tasks, and we ended up with weird-looking graphs anyway. So we're like, okay, what do we do about this if you are a tool developer, right? And one of the other things which was interesting about RAPL and obviously the NVIDIA tools was that they would estimate package power, right? So if you have multiple tasks or background tasks running, which is typically the case on a GPU or a CPU because you have OS, other things happening in the background, or display being connected through the GPU or driven through the GPU and stuff, you are not able to isolate what's the cost of your task as opposed to other background stuff. So we were like, okay, we have the instruction data, right? As we said, both the profiling tools on the CPU and GPU side give us that instruction profile. And we now have made this bespoke ground truth energy measurement stuff, which can do fantastically high accuracy, fantastically high sampling rates and stuff. Put those two things together. So we benchmark a set of applications, get a bunch of instruction profiles, and then combine that with our energy measurement, fairly granular, and then use machine learning model to do training and then predict some stuff. So to do that, obviously, we had to create a data set. So again, we went back to Nuke, ran a bunch of instructions, again, a set of instructions and specific counters. So this is the Intel case using vTune. And then we combined across multiple instructions and multiple function stacks to arrive at a unique-ish fingerprint for each of the tasks, and then combined it with our energy data. So that gives us a data set, right? Again, multiple applications, multiple resolutions were profiled in this. And then we were like, okay, what model do we use? And then we experimented with different machine learning models, not deep learning stuff. And we figured out that random forest essentially was giving us consistently more accuracy than anything else. So that's what we went with, packaged it into a CLI tool, and it's available on GitHub. So if anybody wants to use it, go ahead. Again, there's this GPU version as well. It's called GPU Profiler, for lack of a better word. So then, like, how does this fare against comparison? Again, we went back to the benchmarking. We decided not to use any of the applications that we had in our test bench. So we're like, okay, new set of tasks thanks to the motion picture course, where we were able to pull all of the previous student submissions and stuff and use them for profiling. So here we have the results from the CPU side of things. Obviously, we have the hardware, which is the one in blue. The one in kind of teal green is what we are predicting. And the one in yellow, in this case, is RAPL prediction, right? And average being marked in red in each of those bars. So each of those tools are predicting min consumption during the runtime, max consumption during the runtime, and average power over the runtime, right? And we see there's a fair bit of alignment between the average and the min. The max, obviously, we have identified what the issue is, thanks to P cores and E cores. So we're working on a fix for that. But essentially, the idea is it's way more aligned with what we physically measure at the device level, hardware level, right? And then this is the cool bit that I said. So if you have multiple tasks which are running on the CPU, which is typically the case, then RAPL, or similarly Intel's own stopwatch tool, is not able to isolate what the cost of that task is. It'll just predict, this is your package power for this duration, right? Which is not very useful if you're a tool developer. Maybe unless you're running it in isolation or in stuff. So here the idea was, okay, because we are looking at the instructions themselves, and when you have CPU stress, what happens is your frequency gets changed from your max frequency, which it can execute at, and all that sort of stuff. So that gets factored in for our model as well. So it actually does align with what we think the actual prediction or actual cost, energy cost of that model was, right? So that's the cool thing that we are able to do, and we are able to do that for the GPU as well, right? So in conclusion, with 3 minutes, so what we have done is two different directions. So one is to establish what's the end-to-end energy consumption for existing pipelines, how we are able to do that without destroying, or pulling the whole stuff down and integrating a lot of stuff, use of existing interfaces to build an overlay, which can then pull energy data, which can be used for automations. And then secondly, to look at a more accurate way of profiling this, which would be useful for tool developers. Now, the key points why we started doing this is you can't optimize until you know. So you have to measure. And some level of simple monitoring can lead to, energy optimizations if you do build the right automations. On-chip sensors are a good start, but then, if you start optimizing based on that data, you might go down a different rabbit hole than the one that you actually want to go down to. And the granularity is the key enabler for tool developers, algorithm optimizations, and things like that. So in the future, what we want to do is expand the characterization of the displays. As Helio said, there's a bit of work that needs to be done there. Refine the model. As they said, we have identified what the fault is. We have a fix, but it's not fully tested and ironed out, so we haven't released that version yet. And essentially, why we are at SIMT is to, get the industry and the bodies to embrace energy reporting as another metric. And with that, thank you. And also acknowledging all of our partners on the project, as well as the funding agencies, EU and UKRI for UK partners. Questions?
Are there any questions? Again, we use the app, but I don't see, like, by scanning the QR code, you can answer questions. But since I don't see any, if there are any from the floor, I'd be happy to pass the microphone.
Yeah, in the energy data on the LED panels, there's an enormous baseline power consumption just for being on, even when you're displaying black. You know, the vertical axis doesn't start at zero. It's way, way, way above zero, which is really surprising. What is happening in a display panel and or its controller that's chewing up that much energy when it's not making light?
You're probably better off asking the panel manufacturers.
Yeah,
but from what I understand, there's like a lot of circuitry that, runs through that. In any case, there's a lot of, for example, like you need to receive the signal, so you need something that's on all the time. Often you have, for example, transceiver cages with associated circuitry. And yeah, that's typically running. Yeah.
It really seems like deep inspection of that might find an optimization that could be
sure. Yeah.
as powerful as, prediction from the light.
There are some makers that already include intelligent power sensing. For example, a True Performance, who has a store here today, which allows you to look at, for example, I don't know if they have an API available for it, but they have a UI. So what that means is over the network, you can say, okay, like my panel is on, it should probably not be on right now, and I should fix that. But yeah, it's obviously something that we'd like to, raise awareness about and do more for.
Appreciate that. Thank you.
Of 30 seconds.
Is there another question here? If not, we'll have 30 extra seconds. Thank you, guys.
Thanks.